Welcome. Today we're looking at families of polynomials. Families like these guys. What a bunch they are. Look at these guys' eyes. Wait, what? So we're going to be able to recognize differences between polynomials with odd powers, x5, and those with even powers, x6. So just in general with families of polynomials, the graphs that have got odd powers have got similarities, and the graphs that have even powers have similarities as well. And then there are some clear differences between even powers and odd powers. So to first take a look at odd degree polynomials, the odd degree polynomials are sketched over here, or at least a couple of them are. x3, x1, x1, x3, and x5. x3 is one there. And there are some similarities between these guys. They have the same long-term behavior. So if x is approaching positive infinity, y is approaching positive infinity. And similarly, if x is approaching negative infinity, y is approaching negative infinity as well. The other thing to note is that they all pass through -1, 1, -1, -1, 0, and 1, 1, and they all have a stationary point of inflection at the point 0, 0, except for y equals x, because it's a straight line. But of course, we can transform this guy and make it change a little bit. And it's really easy to do, or relatively easy to do when it's in this form here. Transformation we'll have a look at as a definition. So first of all, n needs to be an odd number, an odd positive number, n being this guy. That way it's an odd polynomial. There'll be a stationary point at positive hk, even though there's a negative out here, because when we rearrange that, set it equal to 0, it would become positive. And then depending on whether a is positive or negative, the direction of the curve changes. So these three have all got a positive a value. A negative a value might look something like this. It's not particularly well drawn, but you get the idea. And then x and y intercepts are found in the usual way. So x let y equals 0. So that's our odd degree polynomials. To take a look at our even degree polynomials, these guys are sketched over here. That's x2, x4, x6, x8, etc. The same long-term behavior exists again. So as x approaches positive infinity, and when x approaches negative infinity, in both cases, y is approaching positive infinity. That's because when we think about it, for x squared, if we square a negative number, we're going to get a positive number. There's a turning point, a maximum or a minimum at 0, 0, and the value of a determines whether it's a maximum or a minimum. Alright, so if a is a negative number, we'll have a negative polynomial, which means we have a maximum point. The axis of symmetry of these guys is going to be when x is equal to h. Alright, so we could draw a line down the middle when x is equal to h, and h would be equal to 0 in the case there. And it would be symmetrical in between those two lines. I obviously have not drawn that symmetrically. As we know, 0, 1, or 2 x-intercepts, and we can use the discriminant if it's a quadratic to work out how many of those. And then there's 1 y-intercept. We can look at some examples. So in this first example, we're going to sketch this guy here. The first thing that you're going to hopefully recognize is that n is 5. So we can say n is equal to 5, therefore it's a odd polynomial. So that means it's going to look something like that, or maybe if it's positive like that. So we need to first up state the point of inflection, the coordinates of the point of inflection, and from the theory we learnt that the point of inflection would be at POI would be at -2, -7. Then we need to find x and y intercepts, and we should be able to sketch. So x intercept, we let y equal 0. So x int, so 0 is equal to 1 over 16, x plus 2, all to the power of 5, take away 7. So to find that, we're going to add 7 to both sides. So 7 would be equal to 1 over 16, outside of x plus 2, all to the power of 5. I'm going to times both sides by 16, because timesing by 16 would mean that 16 would go on the top of the denominator. That would cancel out to be 1, and then we'd times by 16 here. That would leave us with 112, I think, yeah, 112 to x plus 2 all to the power of 5, and to get rid of the 5 and solve for x, we need to take the fifth root. Obviously if it was 3, you'd take the third root. If it's 1, you just take the square root. Sorry, if it's 2, you just take the square root, my mistake. That cancels out with that, and we need to take the fifth root of both sides. So we've got the fifth root of 102, and then we need to subtract 2 from both sides. I'm going to do it in the same step. So that means we've got an x turning point, an x coordinate of the x intercept rather at the fifth root of 112 minus 2. That's going to be a little bit confusing, so we can say that x is approximately equal to squiggly lines 0.6, just so I've got an idea in my head. So our x intercept would be root 5, the fifth root rather of that, and 0. Find the y-intercept. We let x equals to 0, and you can do this yourself if you like. 1 over 16, 0 plus 2 all to the power of 5 minus 7. I'm just going to tell you, you can check it if you like, but y is going to be equal to negative 5. So I've got a coordinate at 0, negative 5. Now go ahead and sketch this guy, because we've got all the information that we need to know, except we need to think about whether it's a positive curve or negative curve, and that depends on the value of a. So the value of a is positive, so let's take a look at what that means for the sketch. When we're sketching, we need some Cartesian plane. We know we've got some points at negative 2, negative 7. I'm going to go ahead and label these axes. Negative 2, negative 4, negative 6, negative 8. 2, 4, 6, 8. Same with the negatives. I've already got the arrows and the x's there, so we're all good. And then 2, 4, 6, 8. So I've got points at negative 2, negative 7. So negative 2, negative 2, 4. It's negative 2 here. And then negative 2, 4, 6, 8. We'll leave this guy here. We had x intercept at approximately 0.6. So that's 2 there, then 1 would be about there, 0.6 would be about here. And then we've got a y-intercept at negative 5. 2, 4, 5 would be here. Alright, so we can now go ahead and draw that. We know this is our point of inflection. So we're going to come down. It's going to be quite narrow. It's a positive shape because a is a positive number. Come down, we've got our point of inflection, and then down we go again. Not too bad a drawing. We'd probably lose marks over here for a lack of clarity. We need to then label these points. This point here I need to keep in exact form, not in decimal form. So this point here I'm labeling as, what was it, minus 2 and 0. And then this guy here was negative 5, 0, negative 5 in fact. And then this one here is negative 2, negative 7. And we're done. We might want to fix up the straightness of that line. Moving on to our second example. We need to sketch the graph of this guy here. First up, we're thinking that n is a positive number. Sorry, an even number. I keep getting that confused. So we've got an even polynomial. So we're going to look something like this or something like that on the set of axes. The turning point or the stationary point, we call it SP. We read it off. Negative 5, negative 1. So stationary point, negative 5, negative 1. Is it a maximum, a minimum, a point of inflection? It's a turning point, so it's going to turn around. Because a is a positive number, a is equal to 1, a is a positive number, it's going to be a minimum. It's going to look like this. And so we call it a min. X-ints, to find the x-intercepts, that is, we let y equals to 0. And for the sake of time, I'm just going to go ahead and put the answers right in. So So to pick it back up at this point, we've got plus or minus 1 take away 5. The reason that's happened is because we've taken the fourth root, and the fourth root, like the square root or the sixth root, is going to give us plus or minus 1 here. So we're going to end up with two solutions. Solution 1 is x will be equal to negative 1 take away 5. Next 2, which would be equal to x is equal to positive 1 take away 5. So that's x equal to negative 6 and x equal to negative 4, or negative 6 comma 0 and negative 4 comma 0. So to now sort out the y-intercept with x equals to 0, I'm going to pause again and just do the working out to save us a bit of time. And we end up with y is equal to 624, so the coordinate is 0 comma 624. And now we should have all the information to be able to then go ahead and sketch that guy. So when we sketch, we're going to go ahead and draw our axes. I'm just thinking about whereabouts those things would occur. The y-axis, so if you do a little sketch over here, the turning point is going to be down in this quadrant. The x-intercepts are going to be roughly here and here, and then the y-intercept will be way up here somewhere. So I don't really need to draw these parts. So what I'm going to do is draw it like this. And the scale is going to be a little bit funny here, because we're going to have a y-intercept way up here at 625. We're going to have our x-intercepts at negative 6, 0 and negative 4, 0. And then we're going to have our y-intercept, our minimum point at negative 5, negative 1. So it's going to be negative 5 there. That scale's not quite right. The thing is that this scale is quite funny, so negative 1 is going to be all the way up here, more or less on the axes there. I haven't labelled my axes, so let's do x and y. And I need to put in that as, I'll label those in a minute in fact. So if we grab out a pen, we're going to have a point here, we're going to have a point here, we're going to have a point here, and we're going to have a point way up here. And so the scale I've used is probably going to look a little silly, but we're going to come down something like this, and hit through there, through here. We're going to flatten right out. Oh, I've not drawn that very well at all. But you get the idea. I just haven't quite cut through. It's a little bit hard to do with this drawing pad I'm using. It's a positive graph, so that's a minimum point there because A was a positive number. Sweet. To finish off transformation, there's a definition there. I'd like you to copy that down into your book if you haven't already got it. There's the original form here, which is y equal to x, and then a transformed form, which is y equals 2x plus 3. Otherwise, I think that just about does us for today. See you guys back in class.